Now let me introduce you some useful functions. The first function I would like to introduce to you is the unit gate function. Unit gate function is defined as the gate path of unit height and the unit width. The interval when the function value is 1 is when x greater than -1/2 and less than 1/2. When x is -half or +half, the value of the function is half. When x greater than half or less than -half, the value of the function is 0. This function is centered at the origin. It is shown in this figure A. You can see from the shape, so this function is just a rectangular function. So therefore we use the first few letters of rectangles, R-E-C-T, rect, to represent this function. It's a rectangular function, also called unit gate function. The unit gate function in figure B, the gate path in figure B is the unit gate path, rectangle x, expanded by the factor A along the horizontal axis. So therefore, we can express this function as s/tau. So this means time expansion. If x times tau is time compression. Observe that tau, the denominator of the argument of rect x/tau, indicates the width of the path. So similarly, you can consider the denominator is 1. So therefore, the width of the function is 1. The next function I would like to introduce to you is called unit triangle function. Unit triangle function is defined as a triangular path, here it's shown here, of unit height and the unit width, centered at the origin. From the definition, you can see we use the data to represent the triangle function. You can see from the shape is like a triangle. Therefore, this is the notation for triangle function, delta x. When absolute value of x is greater or equal to half, the value of the function is 0. When x is less, the absolute value of x is less than half, is 1 minus 2x absolute value. So when x is positive, between 0 and a half, the function is 1 minus 2x. When x is between -half and 0, the function value is 1 plus 2 times x. The function in figure B is the unit gate path expanded by a factor of tau. We know x/tau, it means time expansion. The unit triangular function is expanded by a factor of tau. Same for the gate path, the denominator tau of the argument indicates the path width. The path width is tau. The last function I would like to introduce to you, it is called sine or argument function. It is denoted by SINC, sinc x. This function plays an important role in signal processing. is also known as filtering or interpolation function. This function has many properties. So the definition is sine x over x. First, this is an even function of x. You can see from this figure A, this function is 0 when our sine x is 0, except when x is 0. So we know sine x is 0 when x is negative and plus and the potent negative. So n times pi. So n will be positive integers. So therefore, this function is 0 at pi, negative pi, 2 pi, negative 2 pi, 3 pi, negative 3 pi, and so on. The function value when x is 0 is 1. We can use L'Hopital's rule to calculate the value when x is 0. It will be, if I take a limit when x approach 0, then we see we have the case, so 0 over 0. So therefore we need to use L'Hopital's rule to take the time derivative, the differentiate both the numerator and denominator to be cosine x. So this is 1. So when x is 0, cosine x is 1. The think x is the product of an oscillating signal sine x of period 2 pi and monotonically decreasing function 1 over x. Therefore, the think x exhibits damped oscillations of periodic 2 pi with the amplitude decreasing continuously as 1 over x. This figure A shows the sinc function. Observe that so sinc function is 0 for values when x are positive and negative integer multiplies of pi. The figure B shows the sinc function 3 omega over 7. We know this function is 0 when our 3 omega over 7 is positive and negative integers times pi. So that's when omega is positive and negative 7 over 3 and pi. So therefore, the first Diderot's function occurs when omega is 7 pi over 3. So now let's look at the figure A. So this is the function 1 over x. Here, 1 over x. This is the function, so negative 1 over x and negative 1 over x. Then you can sync the functions 1 over x and negative 1 over x. they serve as the envelopes of the think function. So the think function is Bayesian 1 over x and negative 1 over x. I have a drill for you to practice. Sketch a rectangular function, the gate pulse function, x over 8. B, triangle function, omega over 10. C, sinc function, filtering function, or interpolation function, 3 pi omega over 2. The last one, the think function, the think t times rectangular function, t over 4 pi. In this example, I will show you how to find the Fourier transform of the rectangular function. So that is the gate pulse function. So this is the gate pulse function expanded by a factor tau from the unit gate pulse. I will show you the calculations using MATLAB. So here, let me directly show you the result. The Fourier transform of the rectangular function expanded by a factor tau is tau times sinc function omega tau over 2. We know for sinc function, when the omega is 0, the function value is 1. Now, this function is scaled by tau. So therefore, when omega is 0, the value of the function is tau. We also know for sinc function, the function value is 0. So whenever omega tau over 2 is equal to positive and negative n pi. Therefore, in this case, we know this function is 0 when our omega is plus, so positive, negative, 2 n pi over tau. So therefore, the function is 0 when 2 pi over tau, negative 2 pi over tau, then 4 pi over tau, negative 4 pi over tau. The Fourier transform of x, the function transform, the Fourier transform x omega exhibits positive and negative values, but the real values. We can consider a negative amplitude be a positive amplitude with a phase negative pi or pi. We use this observation to plot the amplitude spectrum of x omega and the phase spectrum. So wherever the function value is negative, when omega is 0, the phase is negative pi. When omega is negative, the phase is pi. So to make the phase spectrum to be an odd function of omega. Now let's think about the bandwidth of the rectangular function of the gate pulse function. The spectrum of the gate pulse function is shown here in figure B, so x omega. So from the spectrum, we can see it peaks. If we look at the amplitude spectrum, it peaks at omega 0 and decays at high frequencies. Therefore, we can consider the rectangular function of the gate pulse function is a low pass signal. with most of the signal energy is in the low frequency components. Then what is the bandwidth? So we know the bandwidth is defined as the difference between the highest frequency and the lowest frequency. So clearly here, so the lowest frequency is 0. Then what is the highest frequency? So when we look at the spectrum, it extends from 0 to infinity. So technically, so the bandwidth of the rectangular function or unit pulse function is infinity. However, so much of the spectrum is concentrated within the first lobe from omega 0 until 2 pi over tau. So therefore, we can give a rough estimate of the bandwidth of a rectangular pulse of width tau. So it is 2 pi over tau. If we consider this in frequency with unit hertz, so omega, okay, so bandwidth, okay, is 2 pi over tau. So we consider the unit is a hertz. Okay, so F will be so 1 over 2 pi. So W over 2 pi, so will be so 2 pi over tau divided by 1 over 2 pi. So that is 1 over tau. So here you can notice the reciprocal relationship of the path width and its bandwidth. Let's see this example. Find the Fourier transform of the unit impulse function delta t. We can find the Fourier transform using the definition. So later on, I will also show you how to do it in MATLAB. So based on the definition, so Fourier transform of delta t is the integration from negative infinity to positive infinity delta t times exponential negative j omega t. We know the property of the unit impulse function. So this function is, it has values only when t is 0. Then when t is not 0, the function value is 0. So therefore, we can use the sampling property of the unit impulse function. So when t is 0, the exponential 0 is 1. The figure B shows the Fourier spectrum of the unit impulse function. Therefore, we know the Fourier transform of the unit impulse function is just the 1. It means so the function is 1 across all frequencies with phase 0. Now let's see another example. Find the inverse Fourier transform of delta omega. Again, we can use the definition of the inverse Fourier transform, and I will also show you how to calculate the inverse Fourier transform of delta omega using MATLAB. But here, let's use the property using the duality property. As I already showed you that the Fourier transform of the unit impulse function, it is 1. If we use the duality property, then we know, so we can switch, okay, switch the two functions. We know the function 1 its Fourier transform in the frequent domain will be 2 pi times delta omega. So this is the duality property. So therefore, we know the inverse Fourier transform of delta W will be, okay, let's write in this direction. It is 1 over 2 pi by using the linearity property. So therefore, the inverse Fourier transform of delta omega is 1 over 2 pi. Then we can also think that the function when xt is 1, its Fourier transform is 2 pi times delta omega. This example is to find the inverse Fourier transform of delta omega minus omega 0. Again, you can use the definition to find the inverse Fourier transform. And I will also show you how to use MATLAB to calculate the inverse Fourier transform of delta omega minus omega 0. Then I will show you how to use the properties of the Fourier transform to find the inverse Fourier transform of delta omega minus omega 0. The property we are going to use, it is the frequency shifting property. We know from the earlier result, we know the inverse Fourier transform of delta omega is 1 over 2 pi. Then based on the frequency shifting property, we know if this function is shifted by omega 0 in the frequent domain, then in the time domain, we just need to multiply the function by exponential j omega 0 t. So therefore, the inverse Fourier transform of delta omega minus omega 0 is 1 over 2 pi exponential j omega 0 t. This example is to find the Fourier transform of the everlasting sinusoid cosine omega 0 t. We know using the Euler formula, we know the cosine omega 0 t is half exponential j omega 0 t plus exponential negative j omega 0 t. So based on the previous result, okay, we know the exponential, so j omega 0 t is Fourier transform just delta omega minus omega 0. Okay. So for this one, okay, so it will be delta could be 2 pi delta omega minus omega 0. Okay. So for this one, we just need to change this omega 0 to negative omega 0. So therefore, we know so its Fourier transform will be 2 pi delta omega plus omega 0. Okay. Then divided by 2. Then we have this result. The Fourier transform of the cosine omega 0 t is pi times delta omega plus omega 0 plus delta omega minus omega 0. The spectrum of the Fourier transform of cosine omega 0 t consists of two impulses at omega 0 and the negative omega 0 as shown in the figure B. This result also follows from the quantitative reasoning, and everlasting sinusoid cosine omega 0 can be synthesized by two everlasting components. So exponential j omega 0 t and exponential negative j omega 0 t. So therefore, the Fourier spectrum consists only two components of frequencies. One is at omega 0, another one is at negative omega 0. This example is to determine the Fourier transform of a periodic signal xt using a Fourier series representation. We know for any signals, periodic signal with a period t0 can be represented by using the Fourier series. If we use the exponential Fourier series, so xt is equal to the sum of n from negative infinity to positive infinity, so dn times exponential jn omega 0 t. Omega 0 is a fundamental frequency. Omega 0 is 2 pi over t0. T0 is a period. Now let's take the Fourier transform on both sides. We know the Fourier transform of xt is x omega. As we calculated earlier, the Fourier transform of exponential j omega t is 2 pi delta omega, so this is omega 0, so omega minus omega 0. So therefore, the Fourier transform of exponential j n omega 0 t will be 2 pi delta omega minus n omega 0. Then we use the linearity property. We know the Fourier transform of xt is just 2 pi sums n from negative infinity, positive infinity. Then at the end, it is still the coefficient of the exponential Fourier series. Then times the impulse function delayed by n omega 0. This example is to determine the Fourier transform of direct delta impulse train dot t0 t. So the period is t0. So let's use its Fourier series representation to find the Fourier transform. As we know from the previous example, we know that for periodic function, so x omega is 2 pi sum and from negative infinity to positive infinity, so dn delta omega minus omega 0 omega n omega 0. Okay, then I think I have already showed you this example when we discuss the Fourier series. Then we know also dns is just 1 over t0. So therefore, we have the Fourier transform of this function dot t0 t is just 2 pi over t0 and from negative infinity to positive infinity dot omega minus n omega 0. We know, so this function we know that the 2 pi over t0 is just omega 0. So therefore, we know for this function, it's just the train scaled by omega 0. Now the frequency, the period t0 become the frequency omega 0. This example is to find the Fourier transform of a unit step function, so ut. I just showed you the result without the calculations. I will show you how to get this result using MATLAB. The Fourier transform of the unit step function is pi delta omega plus 1 over j omega. This example is to find the Fourier transform of the signal function when t is positive, its value is 1. When t is negative, its value is -1. So again, I just show you the result, and I will show you how to get this result using MATLAB. The Fourier transform of the signal function is 2 over j omega.